you see this like take a tumbleweed, let me know.
Yep.
Thanks. All right, so basically what we have left in our spectroscopy is to understand both the lines and the things that modify the shapes and depths of lines and the relative strengths of lines, which we've talked about in a great detail in terms of the atomic physics. Okay, we talked about line broadening profile. We talked about so the natural width, if you will, and we talked about the oscillator strength and how this is related to the atom itself, so that different transitions within an atom have different strengths or cross sections, and they have different widths depending upon the various decay channels and their Einstein A coefficients that are involved. And we of course talked about fine structure and seeing multiplets and things like that, to which there were those the final page of all the atomic stuff was the energy diagrams, Grotrian diagrams, which showed all of the different spectra and the families of the spectra, like the type 1a, lithium-like or sodium-like, etc., etc., isoelectronic configurations. But then you have to take those atomic, that atomic physics, and you have to put it into the gas physics. So now we've talked about the gas physics quite a bit, and the radiation field a bit. So what we want to know is, okay, now that you have an atom which has fine structure to it and oscillator strengths, and it has ionization energies and ionization, or I should say excitation potentials and whatnot, and all these things, how does that manifest itself when you get into the gas environment? So combining the gas environment and the atomic physics together to get what are absorption profiles. Okay, and so what we're going to find out is that there's multiple things that go into modifying a profile of absorption. Okay, so the first page of what we're calling line opacities, these notes, is just basically a review of the definition of a cross-section. All right, and you remember that column density times cross-section is what gives you the opacity, or the optical depth. That tau at a given wavelength was the column density times the cross-section, which is a function of wavelength, and at those cross-sections, the natural cross-sections look something very much like this. Anybody remember the name of this profile? A Lorentzian, correct? And its width depended upon the damping constant. The damping constant was the sum basically of all the decay channels and the Einstein A coefficients. All right, that's the leaning tower of absorption cross-section. My bad, sorry about that. Okay, so effectively then you also had bound-free transitions, and in a bound-free transition you might see something like this for the cross-section. This would be a free-free, this would be a bound-free, which is basically ionization. You'd have the wavelength getting higher in energy, the photon higher and higher in energy, you meet the threshold of ionization, cross-section peaks at that threshold, and then as you go to higher and higher and higher energy photons, the cross-section would diminish, and I think it goes as lambda to the cubed. And so you'd have these different cross-sections, and if you're going to get an absorption line, it would be something like this, okay? And if you were going to see an ionization edge, your spectrum might be something like this, and then it would recover. And in optical, we saw this as something called the Balmer break. Yes?
Is it supposed to be bound or free? Did I miss something?
You did. No. I mean, you caught it. Thank you. It's bound. Okay. So I lambda over I continuum lambda was something like this. All right. This was very narrow, about 10 to the minus 4 angstroms in width. All right. Where this edge, literally, this could go for 1,000 angstroms. Okay. So the Balmer break, and then this would recover, or it could be the Lyman break for n equals 1 absorption. In this case, n equals 1 electron being ionized happens at 912, and then you might be down here at 600 angstroms later. 300 angstroms away, you start to get the recovery. Okay, and so you see that these bound free, or what we call sometimes we call them continuum, they change very global, long wavelength variations in the spectral shape. And the bound make very narrow ones. Okay, what we're going to talk about today are the bounds, and then when we come back on Thursday, we're going to talk about the bound frees. And the bound frees are what govern the overall shape of the spectrum. Okay, what we call the continuum. Okay, now we also know that tau is equal to chi lambda ds, well, d tau, okay, where this was the opacity, but we were able to do, if you remember the very first days of class, we did some manipulations which showed that, in fact, you could get tau equaling n times the cross-section. All right, and I believe that's because chi lambda was equal to the number density times the cross-section. All right, so we need to know the number density of that exact type of absorber. So this could be, for example, again, if you're talking about an H alpha line, this is the number density of neutral hydrogens that are in the first excited state times the cross-section for the H alpha transition. Okay, that gives you the opacity as a function of wavelength, and then you could take that, integrate it over the length of the cloud to get the total tau, but we found out that in fact that's the column density of that particular type of ion times this cross-section. And then this was e to the minus tau lambda.
So is it the number density or the column density?
This is the column density. This is the number density. Little n's the number density. Okay. All right. But what we're going to find out is that other things besides the natural broadening of the profile actually also contribute to broadening an absorption line, a bound absorption line. Okay. So what are those? Yay, the blue works. I have a list of them right here. Okay. First of all, you have the natural broadening. All right. And what kind of function is that?
Lorentzian.
A Lorentzian. Okay. And that Lorentzian depended upon the wavelength of the transition, the oscillator strength, and the damping constant, if you remember what that was. Okay. The second one you have is the thermal. And this turns out to be a Gaussian, okay? And the Gaussian depends upon the mass of the ion and the temperature of the gas, okay? Now, if you remember right, the three-dimensional velocity distribution of an ion, of any ion was the Maxwell-Boltzmann distribution. But if you looked at it collapsed in one dimension, which would be the line of sight, it turned out that the Maxwell-Boltzmann distribution collapsed in 1D to a Gaussian. Okay, so you have some atoms moving toward you, some moving away from you, and the distribution of those numbers, the distribution function is a Gaussian. So basically, not only do you have a natural broadening, but you'll also have a Gaussian broadening, and you have to convolve them. You have to convolve these two functions together to get the final broadening. Well, in addition to that, you might have what's called turbulent broadening, or what you might call, sometimes people call it bulk broadening, bulk motion broadening. Okay, this is more like convection. This is where your gas, parcels of your gas, are actually carried along systematically in some distribution of velocities. Okay? Now, this is based upon something that we call V-turb, for the turbulence velocity. That could be a function of depth in the cloud. It's very complex. But what people do almost without fail always is they assume that it's a Gaussian. Okay? So I want you to put in your notes assumed. Because if you assume it's a Gaussian, the mathematics simplifies dramatically. Now, if you have a complex gas flow, like a supernova wind, okay, where your density and, bless you, your density and your velocity is mapped out along the line of sight in a very complex model of flow, then you're talking about something that can really modify the shape of a profile in a very crazy way. Okay. But in stellar spectra, this turbulent broadening, given by some mean turbulent velocity of the mixing layer of convection, and usually assume that that is causing a Gaussian. Okay, so now you're convolving a natural broadening, a Lorentzian with a Gaussian with a Gaussian. All right. And finally, last but not least, important for stars but not for the IGM or the ISM, is pressure broadening. All right. And this is actually extremely complex. All right. This turns out also to give you a Lorentzian, believe it or not. Okay? And it's dependent upon its own set of functions. It depends upon the electron density, because it depends upon collision rates, depends upon the density of the ion itself, and then it depends upon something I'm going to call little gamma of n. Okay? Now this n is an index for the type of broadening, pressure broadening, that we're going to talk about. We're going to talk about Stark broadening, linear Stark, quadratic Stark, van der Waals, and each one of those is given an n as an index. So this little n here is the index of what the type of pressure broadening is. It's basically due to collisions. Okay? Everybody with me? And last but not least, not mentioned on here, is if you have a star that's rotating rapidly, you can get rotation broadening. Okay? This is its own beast. In fact, I don't even know what the name of this function is, because it's not a Gaussian and it's not a Lorentzian by any means. So I'm going to call it little f. It's just a function. And this is going to depend upon v rotation and the sign of the inclination. Okay? All right. Now, that's in the simplest case. also, in the more complex case, you have to account for the fact that if the stellar disk that you're observing has a constant temperature and it's rotating, then it only depends upon the rotation and the inclination of that rotation with respect to you. But if you include limb darkening, everybody's heard of that? Okay, the fact that when you look at the edges of the limb, that you're actually seeing cooler layers, and so it's not as bright, not emitting as many photons as intensity. So if you include limb darkening, then there's some additional functional forms here. And then, of course, if you have large temperature variations, so this can become complicated too, but the simplest case is you just assume you have an isothermal disk. Okay. All right. So, you convolve all these functions together, and that's how you get the final absorption profile. Okay? So we know that we can write tau as, for natural broadening, tau for natural broadening is equal to the column density times the sigma for the natural broadening. Okay? Well, now let's think of this as being the total sigma, the total cross section. And basically what you're saying is that what people like to do is they like to replace this now with something called the total absorption cross section. And so instead of writing it as sigma, they'll write it as alpha. Okay? Now, different books, different authors do different things. If you go to the most used book on stellar spectroscopy, it's by a guy named David Gray, and he uses alpha. All right? If you go and you use one of the other most famous ones by Dmitry Mihalis, you also find that he uses alpha. So it's common, but sometimes you'll see it written as sigma, as total. Alpha lambda is sigma natural. So it's just a dot for convolving, is that right? Can't remember what it is.
In your notes you use a star.
Yeah, I think it's a star, thank you. Convolution with the thermal broadening, G thermal, convolution with the turbulent broadening, convolution with the pressure broadening, convolution with the rotational broadening. It's quite a convolution. Okay? Now, turns out you don't have to know all this physics for every single line. Okay? I would say 90% of the time, for most, especially for most metal lines, okay, this is particularly true for almost all metal lines, you only need the natural and the thermal. Or perhaps the turbulent. Okay. In my business, when I study the intergalactic medium, I only have to deal with the natural and the thermal broadening. I have some cloud out there. A bound-bound transition has a natural broadening because of the atomic physics. And then the gas cloud has some temperature or something like that. And so I just have to convolve the natural and the thermal together. Okay. If I'm studying stars, somebody like Sten, I have to consider the turbulent as well. Okay. Now, if I am studying stars where the pressure is high, the number density is high, then the particles are in a higher density gas. So if you go to a type 1A luminosity class, the pressure is low, right? Surface gravity is low, the pressure is low, and you don't get any pressure broadening. Well, it's minimal. Go to a main sequence star, particularly getting down in a K star or a G star. Log G is high, 10 to the 4-ish or so. Pressure is very high. The density is therefore high. Collisions are therefore much more, timescales between them are much smaller, and you have to account for pressure broadening. And we talked about this at the beginning of the class, that stars that are main sequence stars have high log G will have broader absorption lines than, say, a star of the exact same temperature, which is a giant star. And that just comes down to the log G, which comes down to the pressure, which comes down to the number density, which comes down to the time between collisions. Okay. So if you're talking about certain transitions in main sequence stars, you have to worry about pressure broadening. Okay. For the most part, the transitions you have to worry about the most are hydrogen, because hydrogen is so light and is so abundant and is affected most strongly by free electrons, more so than the metals, that you really, if you're getting into the hydrogen lines in a main sequence star, you have to include the pressure broadening. Okay? And then what we're going to find out is that stars that are in a certain region of the periodic table are fast rotators. All right? Think stars that are O, B, A's, and sort of F's are, for the most part, have a wide variation in rotation speeds, whereas the G types and the K stars seem to have a very narrow range of rotational speeds on average. When you get to the other part of the spectral classes, you find that there's a wide variation in the rotation speeds, and so sometimes you'll be observing an absorption line, and you'll find out that it's broadened even further by rotation. All right. Now, the thing is you get to be a pro, is you can look at a profile and you can tell yourself that's from rotation, or that's from thermal broadening, or that is from pressure broadening. And the reason is because velocity turbulence and velocity broadening from thermal, those are Gaussian in nature. They affect your profile to look more Gaussianish. Okay? Pressure broadening is Lorentzian. Okay? If you remember right, a Gaussian looks something like this, and a Lorentzian looks something like this. That's a really bad rendition again. My apologies. Sorry. I feel like a kindergartner. I got a thumbs up? Okay. Straight up, Chris. Did pass on your final exam. So now you know the level at which you have to draw things on the exam. There you have it. But anyway, you get the point. They're very narrow, and they have these very broad wings. And the Gaussians are that very, very classical, normal bell-shaped curve. So when you see absorption lines that are the inverse of that, they look like a Gaussian, you're like, oh, this is dominated by velocities of thermal or turbulent. If you see something where your profile has this central core and these very broad wings, then you know that pressure broadening is kicking in. Now, even though the natural broadening is a Lorentzian, remember that this width is extremely narrow. Okay? The atomic physics comes into play only in a very narrow region. Okay? And whereas these things, remember, these can be on the order of an angstrom. Okay? So you can see that the core of the line and then the Gaussian broadening is tremendous. Okay? Well, maybe I should say 0.1 angstrom. And I've got some pictures of this. All right, so anyway, that's what this page here is trying to cover. And I call them F's here, but here I went ahead and put the L's and the G's to help emphasize the functional forms for you. Hope you don't mind that. Okay. Okay. So let's look at these notes. I think at first I talk a lot about the natural broadening. Okay, and so this is a review basically. I don't want to go through it again of the Einstein A coefficients and the oscillator strengths if you turn the page. And then here is the full-blown oscillator strength for hydrogenic atoms. This one that says hydrogen stake. So if you want to look at the formalism, here it is. I really, it's all in my typed up LaTeX notes now, so you can see all the formalism. I don't want to go through all that again. Okay, then here's the derivation of the line blending profile. Okay, in the handwritten notes, and then here is the Lorentzian shape, and then there's this little inset. It was in the notes we talked about earlier. The difference between a Gaussian and Lorentzian for the same width there. Much better than my diagram. Okay. All right, and then here's the discussion of the damping constant, and yak, yak, yak. And then we finally get out at the very bottom of the page here, where there's this box. We get out the final shape of the cross-section for natural broadening, okay? And that it is a Lorentzian, and that it depends upon the oscillator strength, as you can see here, linear proportion of the oscillator strength, and has some proportionality to the damping constant here, okay? All right. So that gives you the shape with frequency or with wavelength, okay? And then, of course, we talked about the atomic constants. You have the central wavelength for a transition, the oscillator strength, and the damping constant, from which then you can compute alpha natural for each atomic, and that's all atomic physics. Okay. So that we had already talked about earlier in the class. That's why we just blew by it. You're the most excited group I've ever met in my life. It's the end of the semester. I get it. All right. Now, the thermal and the turbulent. All right. This is probably a fairly poor description of what's going on with thermal broadening. What I'm trying to illustrate here is, particularly in this diagram, let's say that this particular profile in the center of this diagram is at velocity of 0. 0. So you've got an atom, it's at rest with respect to you, and a photon comes through at exactly the right wavelength or whatever. Or I should say, a beam of light comes through, and you would see the beam of light being absorbed in that very narrow region, which is 10 to the minus 4 angstroms in width and has these little Lorentzian wings, and that would be the shape of the removed photons from the beam. Understand? Now, let's say I take the atom, all right, and I move it away from you at 0.1 kilometers per second. Okay, so now the atom's moving away from you, same beam, that atom is going to absorb longer wavelengths right there. So you see what I'm saying? It shifted the location of, this is a single atom, it's shifted the location of where those photons are. Okay. Now this is a difference of 0.1 kilometer per second, and it has shifted it, you know, at least 10 widths or so. Okay. So that's what I'm trying to show. And likewise, if I take that atom and having it move toward you, now, instead of the absorbing here or absorbing over there, the atom's moving toward you, it's going to be toward bluer wavelengths. Okay. And so this is basically showing that in this description here, the atom's moving toward you, the photon is removed at lambda 1 minus v naught over c, where v naught is the velocity, and you can get the change in the wavelength here. That would be the observed wavelength, okay? And so you have the fact that when it's moving away from you, it's absorbed at a redder wavelength, and when it's moving toward you at a bluer wavelength. Now what you have to do is you have to consider an ensemble of atoms in this gas, okay? And remember, the line of sight distribution of those velocities is a Gaussian. Okay? So most of the atoms are not moving away from you or toward you. They have a velocity of 0 with respect to you. Some of the atoms are moving toward you, some are moving away from you. Very few of them are moving rapidly toward you, and very few of them are moving rapidly away from you. Okay? So you're taking this narrow profile, right, and you're convolving it with a distribution of velocities. Okay, so you're taking this and you're weighting the peak of this, basically, by the distribution of the velocities. That's basically what the convolution is. And you get out a new function, which is called a Voigt profile, or a Voigt function. Okay, so this page is just basically reminding you that the line of sight distribution is a Gaussian. Okay, and this page is basically demonstrating to you how this is the redistribution function right here. This thermal broadening G function that I've written here on this page with the two figures is written right there. Okay, it's a distribution function that shows you that depending upon the velocity difference, there's this delta lambda d, which is the velocity of the atom, or the mean velocity of the atoms, divided by the speed of light times the rest wavelength of the transition. And so that is equal to c over lambda. The v naught is 2 kT over the mass of the ion. So that's where the mass of the ion comes in, and the temperature comes in. All right? And so basically this delta lambda d down here is this 2 kT over m, and it appears there in the normalization and there in the Gaussian. The delta lambda is the distribution of wavelengths, so you just carry along the delta lambda. And you can see now for hydrogen of different temperatures the distribution that you will actually get. Or here is for different ions with different masses for the same temperature. You can see the distributions. And so you can see here how this redistribution function is going to broaden your profiles. If you've got hydrogen in a very cool gas, it'll be a narrow peaked profile. If you have hydrogen in a very hot gas, it'll be a shallow, broad profile. Okay, if you have hydrogen in a very hot gas and you have that short, broad profile, you will, then if you look at iron, which has a mass that's 56 times more than hydrogen, it's going to have a narrower, deeper profile because the atoms aren't moving around as rapidly. All right, so we've talked about that at the beginning of the class. A lot of times what people do is they talk about something called the B parameter. Okay, so what they do is they define a parameter called the B parameter, which is basically the square root of 2 kT over the mass of the ion. And that is measured in kilometers per second. And so it gives you a feeling of what the width of the line will be in kilometers per second in the spectrum.
So it's not necessarily the thermal velocity. It's just.
Yes, it's not necessary. I mean, in a sense, it's the mean thermal velocity, the V naught. In fact, as you can see right here, Emma, I wrote that it's V naught over C times lambda, or lambda over C times B. You see that?
Yep.
That defines the B parameter. Okay. This is a relationship here on this chart, which shows as temperature goes up, what the Doppler B parameter is for different ions. You can see here the hydrogen line goes way up, and so here are temperatures. Here are spectral types for those temperatures across the top. So you could say, well, for an A0 star, it's 10,000 degrees. The Doppler B parameter for hydrogen ought to be around 40 kilometers per second. Okay, which means that if you convert your spectrum into a velocity spread, it'll spread over 40 kilometers per second. Okay. For an A star, iron has a Doppler parameter of about 4 kilometers per second. So you can see it's going to be a very, very narrow line. If you go back to this diagram here, this was in wavelength space. This is in velocity space up here. Okay. So you can see here, 10,000 degrees gives you a plus or minus 0.1 angstrom width. With that turns out to be a plus or minus 20 kilometers per second width, which is 40 kilometers per second. Okay, everybody with me on that? So that defines the B parameter. So basically, then what people do, just to make life simple, so now you have the distribution function for turbulence, and I've showed you that it depends upon the B parameter or the temperature in the ion, okay, and that's a Gaussian. Then what people do is they just assume that the turbulence from convection is also Gaussian. Some cells are moving forward rapidly, some are moving slowly. The typical piece parcel of gas is not moving with respect to you. All right, and so basically what they do is you have basically, if you look at this page here, here's the Gaussian in velocity space, here's the B thermal. You define here a turbulent B parameter, okay? And so you have a lambda thermal and a lambda turbulent. That is just basically lambda over C times B. And so you have both a thermal broadening function here, okay, that's this one here, and then you have a turbulent one. They're identical except for that the broadening parameter, what's called the Doppler broadening parameters, are different. One is basically proportional to T, the other one's just held at a constant, all right? And that constant can be empirically determined in the spectrum as a free parameter, usually is how it's done, okay? So now, what I want to say to you is you have to understand this, please do, that when you convolve a Gaussian with a Gaussian, guess what you get? A Gaussian. I'm going to do this even better. If you do a Gaussian, which has, let's call it B1, okay, and you convolve it with a Gaussian, which has B2, where this could be the thermal broadening parameter and this could be the turbulent broadening parameter, you get another Gaussian out, thank you, God, which is equal to
B1 plus B2?
B3. It sounded funny.
I just made a stupid guess.
Okay.
Don't worry.
You ever added errors in quadrature? That's because you're taking the error if it's normally distributed of parameter 1 and the error if it's normally distributed of parameter 2, and you're convolving those distributions together and getting out a new normal distribution which has the sum quadrature sum as the new error. Okay, so this would be the turbulent, this would be the thermal, or vice versa. You get out a new Gaussian with a certain width, which is the quadrature sum of the other thermal parameters. That's very, very convenient. That means that this can be combined into a super Gaussian, right? Thermal, turbulent, Gaussian. Okay? Simplified some math for you right there. Now in my business, I don't worry about turbulent velocities. I'm just doing intergalactic clouds or, halo clouds, and we just assume that those are not moving with some kind of turbulent motions within them, all right? We just assume some Doppler parameter and we just go straight ahead and assume that it's all thermal. But we could say that the Doppler parameter we get out of our fits are some quadrature sum. We do that in some cases, actually. But for the most part, in stars, you really need to consider this turbulent broadening because it can be on the order of a couple kilometers per second. All right, so what I'm showing you here at the bottom of this is that your new distribution function is a function of your Doppler broadening delta lambda sub d, where that is equal to this quadrature sum of the thermal and the turbulent broadening. Bing. Okay. Bang, bing, bing. Okay. So now you are left with this. I'm running out of room and I keep losing my eraser. So now what we're going to do is we're just going to convolve the two, the thermal, turbulent. So if we take these three, take these three, right, okay, we have the natural, which is E squared times EC squared lambda, the transition squared times the oscillator strength times this beautiful thing. I'm doing it in wavelength space now for you because we're used to working in wavelength space. All right, and then you have the Doppler, or the broadening one, which I'm going to call F of delta lambda. Okay, that's N for natural, if you will. This is a Gaussian. and it's normalized such that when you integrate over all wavelengths, you get out a unity. Both of these are normalized so that the area under them is unity. Okay. Does anybody remember what delta lambda d is?
B lambda over C.
Okay. What did I just write down? Delta lambda d squared is the thermal broadening component plus squared plus the turbulent broadening component squared. Okay. This is basically 2 kt over m. The square root of that is b. And then this is the turbulent velocity, and this is just the wavelength over c of the transition. Now, what are the two parameters that you get when you observe an absorbent profile? There's two parameters you might not know. This is atomic. You know all these. These are atomic constants. You know the wavelength of the transition. You know the frequency. You know the oscillator strength from NIST. You know the dampening profile. You can calculate that. Boom. This you can't calculate unless you know two things. The turbulent velocity and the temperature of the gas. Well, where do you get those? You don't. These are free-fitting parameters. Okay. So now what we're going to do is we are going to convolve these . And we're going to get out a new function called the Voigt profile. How many people have heard of a Voigt profile before?
I have.
Got a couple hands. I have. Okay. So this Voigt profile is also sometimes known as a complex probability function. And I'm not going to write it all out, but in a sense, if you're only including these three, this is your alpha, right? So you observe a profile like that. Okay? This you've got because you have all the atomic physics data on that profile. If this is H alpha, you look up the oscillator strength for H alpha, you look up the central wavelength for H alpha, you look up damping constant for H alpha, and you calculate, you have this to compute. Okay? Then you have this other function, which depends upon the mass of the hydrogen, some other physical constants like the central wavelength of the transition of H alpha, and you have two free parameters, T and V sub T. Okay? So you guess at your T and your V sub T, you calculate this, you convolve it with that, you get out alpha, then you multiply it by, oops, you don't know the column density either. Well, guess what? There's your third free parameter. Don't know the column density. So I have three parameters that I'm trying to fit here. Temperature, turbulent velocity, and column density. So I guess at those, and I generate a profile, and I draw my profile, and I get out something that looks like this. Ah, crap. That doesn't match the data at all, does it? Well, I think the line needs to be deeper. I know I can get that. I'm just going to crank up the column density. So I guess at a new column density, hot damn. Got it. Okay. All right. Well, it needs to be broader. Where can I get some more broadening? Well, I could crank up the temperature. How about I crank it up 10,000 degrees? I crank it through, convolve it, calculate this. Right? I broadened it too much, and in the process of broadening it, the depth went down because it's conserving this. So it's like, oh, okay, I'm going to add some more column density. Anyway, you play around with it. You monkey around with these three parameters until one day you finally guess them right, and your data goes like this. And you go, hot damn, I know N, T, and V sub T, done. Yes?
Is it always a unique solution?
No. There's degeneracy here. And guess what? I haven't even taught you about yet. We haven't even allowed for the fact that once it goes through the telescope and goes through the dispersing elements of the spectrograph, that blurs the profile even more. So really, this beautiful equation has violence done on it. And we have to modify it even further, which involves another convolution. If you want to do spectroscopy, you better know how to do convolution. That's all I have to say. Anyway, we get ahead of ourselves a little bit. All right. So, any questions about that? So at least what I've tried to do here is show you how you try to get some of the physics. How the physics of the gas modifies the profile from its natural, based just upon turbulent and thermal, and how you would go about trying to find out what the properties of that gas are from your absorption line. It's basically a chi-square problem. Okay, and you generate some code which goes through and tries to make intelligent guesses and narrow down on them, similar to the way you got the electron density. In that case, you used a bisecting method, which is very stable, but you might try some other method. But now you've got three parameters to play with, and you may have some degeneracies. And then you, of course, want to try to understand what the errors in these, how accurate you can be with those, which means you have to juke around and determine some kind of error since it gets complicated. Okay. All right. This page here is another attempt, failed or not, to try to describe how you go from a natural profile here, which has a width of 10 to the minus 4 in angstroms, or this parameter x, okay? And then the column density times the thermal redistribution function, and how when you convolve those, you get out this new function, which is a Lorentzian. That's the third column, tau of x. And then once you put it through the radiative transfer, e to the minus tau, you get out the absorption profile. Okay, that's the process. All right. And we've talked earlier in the class about the curve of growth, how the column density and the B parameter affect the equivalent width that you get out. All right, so I'm not going to review that. And then you have here the model for the turbulence is very simple, showing the convective cells and how you see the solar granulation, and how you assume that this is a Gaussian distribution of velocities that you then convolve in here to get out this complete velocity redistribution function, okay, which is a Gaussian. And some of the evidence for turbulence comes from the fact that if you just use a thermal model on certain absorption lines and stars, you end up under predicting. That's the line here, the thermal model. The thermal model is basically this model with v sub t equals 0, okay? And that when you go to compare the equivalent widths of your lines versus what's observed, you notice that there's an offset there. So that there has to be an additional term in addition to the temperature term. It's a very simple idea, okay? Okay, now we are at the end of, very close to the end. Now, I have no problem that I've spent most of the time on the turbulent and thermal broadening, because 95 to 99% of all the problems you would ever solve, you only have to worry about the turbulent and the natural, and you get out the thing called the Voigt profile. Okay? But if you are going to become a true stellar spectroscopist, you then have to go beyond the basic model, and you have to do the pressure and the rotational broadening. In short, I'm just going to give you the summary, but then we're going to go through it a little bit. There are free parameters here, in this case T, and in this case V turb, okay, and then you have the column density, which is the normalization, okay. Notice that here you have free parameters too, and it's much more gassy physicsy, okay. You have to know electron density, you have to know the number density, so it gets much more complicated, and now these become free parameters in a third function that you're going to convolve. Whereas we had two free parameters here, okay, now we're going to have a couple more free parameters here, and then if we do the thermal rotation, another function to convolve, we're going to have even more free parameters. So you could end up having temperature, turbulent velocity, this gamma sub n electron density. This actually depends upon pressure and temperature, actually. I should say it's pressure and temperature. So you have the free parameters of pressure, temperature again, so, and then you have the rotation speed and the inclination of the star. And you have to fit all those parameters simultaneously to get out the shape of your profile. So it can get very complicated quite rapidly. But my point is to show you this in principle today. Okay. All right. Now let's talk about pressure broadening very quickly. And what I just want to say to you is, if you look at the bottom of this page here, which is assuming a constant scale height pressure, that you get a scale height, okay, and through that argument you can find out that the number density is somewhat related to P over KT. It's the equation of state that you've seen before, right? So the number density goes up as the pressure goes up, and the number density goes up as the temperature goes down. So when you're in cool stars with high pressure, the number density is the highest. And those are the environments where the mean distance between the atoms will get smaller. And as the mean distance between the atoms gets smaller, their electrical impulse on each other and the time they spend near each other will go up. Okay. Now, I'm a guy for gory details, and you are always welcome to go back and study more astronomy whenever you have the free time. Da-da-ba.
Okay.
But what I want to do then is say to you, let's not worry about the derivations. Let's worry about the types of pressure broadening that exist out there. Okay, so this little n that I was talking about, the index, this is Lorentzian. Therefore, it has a functional form of Lorentzian, except now this gamma n goes in this location here. And so what you need to know for each type of physics that's going on with pressure broadening is you need to know what this gamma is. And once you know what that gamma is, you can plug it into the Lorentzian. Now, just like, listen up closely, just like I showed you when you convolve two Gaussians together, you get a new Gaussian with a different width. The same thing happens when you convolve two Lorentzians together. Okay? So basically now, you'll get out a new Lorentzian that will be the sum of this gamma and that gamma. Okay? Quadrature sum. So the easiest thing to do is you convolve the Lorentzians together, then you convolve the Gaussians, and then you convolve those to get the Voigt profile. All right. But here are the different ends. Okay? And here are the perturbers and which lines or atoms get affected. So this is just a summary table for you so that you know. Okay? Linear Stark, resonance broadening, quadratic Stark, van der Waals. Okay? N equals 2 for linear Stark. It affects hydrogen lines, and it's from perturbations of like atoms. I'm sorry, perturbations are protons and electrons. So if you have a hydrogen atom here, it's gonna embedded in the gas. It's the free electrons and the ionized hydrogen, the protons, that are affecting the energy levels inside those neutral hydrogens through electrical impulses that are blurring the energy levels. Okay. Resonance affects all atoms, and its perturbers are like atoms. So that's basically if you have calcium-2 come by a calcium-2, they have a resonance energy with each other, and that causes blurring of the energy levels. Okay, so resonance broadening. Then we have the quadratic Stark. It affects non-hydrogen atoms, basically helium and metals. And the perturbers again are protons and electrons. So Stark is the perturbers are always protons, ionized hydrogen, or free electrons. Linear Stark affects hydrogen. Quadratic Stark is a higher moment of the electric field and affects all the other atoms. Quadratic Stark is not used very often because it doesn't affect atoms that much. And then you have van der Waals. It's all atoms. Perturbers are non-like atoms, mostly hydrogen perturbing non-hydrogen. So these two are for mostly metals. This one is protons and electrons perturbing, and these are all different atoms perturbing different atoms. Okay. So this is what a profile looks like when it has, say, I think linear Stark broadening. Okay. Now look at that profile. First of all, the core does not go to 0. It is not saturated all the way down. You have this little narrow Gaussian core in this width of plus or minus an angstrom or so. Okay? So you're basically seeing this part. This would be minus 1 angstrom, and this would be plus 1 angstrom. And this is the thermal width from temperatures, typically on the order of within plus or minus an angstrom. Now what you've got is you've got a Lorentzian, which has very strong broad wings to it. So this is crazy. I'm going to try to do this. But you get something that looks like this. And it's spread over tens of angstroms. But notice you've got the little Gaussian core here, which comes from the thermal. And now your natural Lorentzian has become much broader because of the pressure broadening of blurring the energy levels out, and you get this very broad Lorentz wings, damping wings. So what I'm showing you is that you should be able to look at a profile now and tell me whether it's thermally broadened or pressure broadened in terms of what's dominating the equivalent width. Clearly, this is a very odd profile that I've exaggerated that you don't see very often. But if you go and look in the sun, this is the H delta line. This is actually Vega, okay? I guess it's H gamma actually, sorry. You can see that it has pressure broadening in it. There's a main sequence A star. And the hydrogen is pressure broadened by impulses from electrons and protons, Stark, linear Stark. Okay. Here is another example of the solar spectrum. This is a metal line, okay? And I believe this is an example of van der Waals broadening. Again, you see the Gaussian core, the pressure broadening itself, you're using and gamma n equals 6 now, and you can see the overall shape is the similar. So you can really tell pressure broadening. Now let's go to this page. This is, I think, the best example that you have here. Okay. You have this H delta line. Here is a B3 supergiant, no pressure broadening, only thermal. You get to a B3 giant, you get some Lorentzian wings, see how they're very broad, and then you get to the B3 dwarf, which is a main sequence star, and you have much even broader pressure broadening. So it really affects the hydrogen lines, the Stark broadening, okay? Okay. You guys are probably like, you're done, Chris. And I am. I wanted to talk briefly about rotational broadening. So it'll only take me a few minutes to cover rotational broadening. So I will cover that when we meet next time. And then I want to talk about the continuum absorption and how that affects the overall shape of the stellar spectrum. Okay? Now, this in itself could be weeks, as you can see from the notes. There's no point in going through that much detail. In the end, if you're going to model spectra, it's going to be in principle exactly as I described here. But if you have to do pressure broadening in your calculation, then you'll include this Lorentzian in your model, and you'll have the free parameter of, oh, this is an H delta line or H gamma line. Hydrogen really is dominated by Stark broadening, so Stark is n equals 2, and then I will look at the formula for what that is as a function of temperature and pressure and put it into my model, and now I have, you know, some more free parameters that I have to deal with in modeling my absorption line. But in the end, you get out some basic physics. Okay? Now, let's say you do that and you get out the column density of hydrogen. Okay, I got a column density for hydrogen. I got a temperature for the gas. I got a turbulent velocity for the gas. I got a column density of neutral hydrogen in the n equals 2 excited state. And I have maybe an estimate of the pressure from the broadening. Okay. Am I very close to understanding that gas yet? Do I know electron density? Do I know the metallicity? All I know is I know one thing about one atom. I know the column density of neutral hydrogen in its first excited state, and that's all I know. So I have to go to calcium lines, and I do the same model on the calcium lines, and I get out the column density of singly ionized calcium in the ground state. And then I go to iron 2 lines, and I get the column density of singly ionized iron in the ground state. And I try to do that for as many of the different transitions, and I'm left now with a temperature, a turbulent velocity, and column densities of hydrogen, singly ionized iron, singly ionized calcium, maybe neutral oxygen. And I'm supposed to take those column densities then and model the gas like you're doing to try to get out the metallicity and stuff like that. I'm not going to be able to get into that in that class. I've shown you how to model the gas, but I haven't shown you that. How do you use the column densities then to constrain the gas? There's just not enough time for that. But that's how you would do it. So just because you modeled one absorption line, don't be so happy. You still don't know squat about the gas. Okay. All right. Thanks for your extra 7 minutes. I appreciate that. We'll see you guys Thursday. And I'm happy to stay after if anybody